So if we set alpha equal to r, which is what I've been leading up to all along, we see that n of d2 in the Black-Scholes formula is indeed the probability that the stock price is in the money for a call in the risk-neutral world. N of d2 is the probability of a payoff when you measure in the risk-neutral world. That's what Black-Scholes is using in the call formula, and the corresponding formula here for the put. So the Black-Scholes assumption is again a log-normal assumption, and we saw this in Chapter 11. It is an assumption of log-normal stock prices, but we don't use alphas, we use r's, and then the n of d2 and the n of minus d2 are, in those models, risk-neutral models, the probability of getting a payoff for a call or the probability of getting a payoff for a put. And these two symbols are explicitly observed in the Black-Scholes put and call formulas. Next thing I want to talk about are confidence limits. How would we develop confidence intervals within the log-normal distribution? So we might define an STL and an STU being a low price and a high price. So that ST low, we can think of this as being the left end point or the lower end point of our confidence interval, and this is the upper end point. And it's typical in a confidence interval, for example, if we had P equal to 5%, we would call the interval that we developed a 95% confidence interval. And what would we do? We would split the 5% in half and look for a left and a right end point, each of which left 2.5% of the probability outside its range. So that's why you see here that SL, the lower or the left end point, and the right end point are defined using only half of P2. Again, that's standard in defining confidence intervals. So we'd call this a 5% or a 95% confidence interval by splitting the probability in half. Now, because of our model for ST, you recall that, that ST, if I write it here, it's S0, and then it's e to the, and now let me just call it simply alpha t. Let me put a little bit of a bar on the alpha so we know it's not the real alpha. It's just a symbol plus sigma square root of t z. So I only use alpha bar as a notation so I don't have to write that long expression of alpha minus delta minus a half sigma squared. Okay? But notice that all of the ST values are driven by the Z values. So the percentiles of the S distribution come from the percentiles of the Z distribution. So in standard notation, we might call this STL, this would be the P over 2 percentile of the ST distribution, and this would be the 1 minus P over 2 percentile of the ST distribution. That's how they're defined. If you think of the ST values in percentile terms, the L value is defined as the P over 2 percentile. So if P was 5%, it would be the 2.5 percentile of the S distribution, and SU would be the 97.5 percentile. So the point I'm making is that the percentiles of this S distribution follow from the percentiles of the Z distribution, 1 for 1. So that when I want the P over 2 percentile for S, I use the P over 2 percentile for Z. Whatever that Z value is, that's the 2.5 percentile, say, that value in my formula will give me the 2.5 percentile value for S. Similarly, I want the 1 minus P over 2 percentile, and because of the symmetry of the normal, instead of using that value, I can just use the negative of the p over 2 percentile. And we do this all the time in normal calculations. We know that the 97.5 percentile of the standard normal is negative the 2.5 percentile value. It's just a symmetry, and that's all we're doing here. And so you see in the formulas that here we're expressing percentiles in terms of the inverse normal. So here, this is exactly equal to the percentile of the normal p over 2. And here, because of the minus, you get between the minus and this, you get the z of 1 minus p over 2 percentile by using the minus. So it's very simple to come up with confidence intervals of S by just identifying the associated percentile values in the z and just sticking them in.